Hello, my name is Kostrzewa, and I would like to talk today about fast failover in Ethernet-based automotive networks. As most of you probably know, automotive interconnects and network infrastructure must face new requirements resulting from new applications. We have high-resolution sensors for autonomous driving. We have new applications like car-to-cloud communication, car-to-infrastructure communication, infotainment. They are all introducing dynamic traffic with large volume of communication, and most of those transmissions are latency sensitive. We have also traffic from legacy components, and all those requirements bring a new challenge. Simply legacy bus-based systems are not sufficient. Their bandwidth is too low and they cannot handle those new applications. Therefore, Ethernet offers the bandwidth promise. It allows you to scale your bandwidth from 100 Mbits to 10 gigabits and more, as well as other benefits as open network capabilities, open protocols. You can share your technology cost because you can use this solutions from other industries, as well as you can use experience of personnel. However, applications of Ethernet in this domain forces you to consider safety. So you have old challenges very well known in automotive systems, which Ethernet must handle and must handle it efficiently. The one example of such a challenge are permanent faults. So in a lifetime of a vehicle, you must assume that it can happen, that the component will fail. Fortunately, it's one failure per component lifetime, and the most standards as per their reach, they assume that the failures won't happen that often, that you will have two components which will fail at the same time, but still you have to think about it. And then you have to offer either fail-safe behavior, so at least contain the error and bring the vehicle to the safe state. But this may not be enough for higher automotive safety levels, as it may not be possible to bring the driver back into the control loop. So whenever a permanent failure will happen in an autonomous vehicle, you would like to have fail operational behavior so that the system continue to operate using existing resources until the vehicle can stop or the driver can take control. So how to achieve these goals? The most straightforward solution would be to introduce a redundant infrastructure. So if we have two networks, in this case 3 new switches, 12 new cables, and 10 new ports, then we can immediately recover because we are duplicating the whole transmissions. But as you see, it's a very high cost. You are providing a parallel infrastructure which is doing nothing useful. And as you recall the numbers from the previous slide, permanent faults are very infrequent. They are happening only once per vehicle lifetime. So therefore, these resources are wasted. A second possibility is to introduce limited redundancy. So to provide redundant paths through the network so that you can achieve some nodes using different roads. And then you would conduct transmissions in parallel through the network. You could do it statically, so you're always using those two nodes, or dynamically, you're switching from one road to another, as in ring protocols or rapid spanning tree protocol. However, also here you have permanent overhead because you have to be prepared in case of dynamic protocol that there could be a safety critical transmission which has to be rerouted, or this transmission is constantly present and you're wasting these resources because you cannot do anything useful with them. And this is especially challenging in cases of, for instance, sensor traffic. So what we would like to do is we would like to decrease this permanent overhead. So we'd like to be able to use those redundant paths for other communication in the system so that we can use them in some significant way and reconfigure the network when failure happens. So to change the routes, block sender, adjust quality of service, but to do it while assuring safe reconfiguration from end-to-end connections done under operational guarantees. So we would like to reconfigure the network at the presence of failure by complying to all application quality constraints, real-time behavior, self-delivery, and without loss of packet and increased time. So in the next slides, I will show you our mechanism for fast failover in Ethernet-based networks. The idea is based on the software-defined networks approach. So we would like to have a protocol controlling the network. A protocol would be a control plane, and data plane would be used to transmissions. But we would like to do continuous end-to-end communication management, continuous coordination between network management unit and terminal nodes and other applications, and monitoring. And those three features are not included in the standard software-defined network. So we have to extend this approach, and as it would, because otherwise it's not sufficient for application safety-related domains, as discussed already in numerous papers which are belonging to the related work. So our idea would be to make decisions based on the global state of the network. So we'd like to know which component failed, which nodes are affected, who is actually transmitting, and then reconfigure exactly these components which should be reconfigured, so fine granular reconfiguration. We would like to use pre-configured settings. So we would like to, at the design time, we would analyze our network, decide on the settings, and only switch between modes at runtime. And also, the switching between modes must be done in the correct order and with correct delays between actions. Otherwise, we could have sporadic overloads, and we could endanger the safety of the system. So in order to achieve these goals, we would propose protocol controlling switches. So we would have clients which are very similar to SDN agents. But unlike SDN, we would also control end nodes to be able to block some centers, or reroute them, or adjust their paths. And we would like to have a network management unit which is managing this network with a main focus on safety. And this is not happening in the case of standard SDN. So to show you how will it work, here is an example of a protocol. If a switch will fail, then monitors in other network components will inform our network management unit about it. And network management unit will know the global state of the network, will know which component, it can deduce which component failed, is it link, is it switch, which transmissions and senders are affected, how important are they, so it can stop some transmissions so that they won't use this component to avoid dropped packets and costly retransmission. It can adjust the settings in the switches to change the rates, to change the routes, and then restart the senders or adjust the senders so that the safety of the end-to-end communication during operation of the system is preserved. The key feature of the implementation here must be configuration latency. So ABNU Alliance proposed 100 milliseconds. There are some other works which are considering 50 milliseconds as a deadline for the reconfiguration. Therefore, while implementing this, we have to decrease protocol overhead. So obviously, a network management unit and client's performance is critical. We have to optimize it. We have to use C libraries, probably with hardware offloading. We would use also UDP-based network protocol to decrease the synchronization time and send the frames with highest possible priority. We have to be sure that they are arriving within the latency required for reconfiguration. We'd also assure the safety of the network management unit, so that, for instance, everyone can reach network management unit in every state. and fail operational behavior of the whole system. For instance, we can run a network management unit redundantly or provide hardware heartbeat protocol from a network management unit to assure that in case of the network management unit failure, we are still safe. Moreover, this approach is built on the standards and is compliant to existing standards from TSN approach. For instance, standard 802.1 QAC introduces path calculation element to send redundant paths. There is also a standard 102.1 QCC, which proposes a central network for configuration of the safety critical traffic. So basing upon those mechanisms, we would enhance them to allow reconfiguration at runtime. So how does it work in the practice? In order to test this, we created a demonstrator setup. You can see the photo on the slide, which is implementing a simple automotive network with Ethernet backbone. It has 4 switches and several sensor groups for autonomous driving. Also infotainment domain and some legacy components which are hidden between MCU domain gateway. And then to implement those components, we used off-the-shelf systems, and we used software-based switches implementing Linux network stack. Our clients at NMU will implement it as a C libraries running in the user space, and we implemented AVB Ethernet scheduling according to the 802.1 QAV and 802.1 QAS standards. And we considered 3 scenarios: a scenario when a sensor group is failing, when a backbone link is down, and when switch is down. And here you see some results. They are depicting protocol overhead, so the time from the moment when a monitor detected the error until the moment when whole network received information from network management unit about the state of the network, about which settings they should use. So it considers the time during which NMU had to assess what is the state of the network. So the failed components which caused the mode change are listed on the x-axis. On the y-axis, you see the latency. As you see, it's very fast. It's in microsecond, below 1 millisecond. Even though we are implementing everything in software, it's also so the latencies vary depending on the amount of components which we have to reconfigure to achieve this. But we can also see that there are some scenarios in which NMU decided that there is no reconfiguration due to the redundancy in sensor groups necessary, and then reconfiguration latency is 0. This won't be possible in case of the standard distributed protocols such as rapid spanning tree or spanning tree protocol, where all nodes had to first agree on the state of the network. They cannot assess what happened that fast. And here we see the same result from this scenario while considering the time necessary for Linux kernel to reconfigure network interface components and its queuing disciplines. This takes a lot of time in Linux because it was not designed for performance, especially not for automotive performance. But even in this situation, we achieve 50 milliseconds, which is a fairly good result with respect to automotive systems. Actually, we can compare these results with other solutions which are available on the market. Here we have a failover time for max 10 switches for different protocols. We have spanning tree protocol and rapid spanning tree, which are all doing it in several seconds. We have then proprietary solutions, which through reducing the topology to simply ring. So if we cannot send to the left, we are sending to the right, achieve 200, 100, and even 50 milliseconds. Note that many of them may not be able to comply with automotive network requirements, which, as you recall, were below 100 milliseconds. And in comparison with those solutions, our fast-based reconfiguration, even though it was implemented in software, is achieving a very good result. It's below 1 millisecond of protocol overhead and 50 milliseconds of the whole reconfiguration due to the fine granular and predefined scenarios. So to summarize, we have shown that there is need for dynamic network reconfiguration and it provides essential cost and performance advantages in critical applications. Protocol timing for access control is critical. Obviously, the time of reconfiguration depends, for instance, on many factors, for instance, on the latency of control messages. But if you are interested, we conducted many tests to test all those factors, and you can see them in the paper. So please refer to the paper. Our results have shown that this approach is feasible for automotive, and actually in the future research it can be extended to handle other situations where we have dynamic workloads, for instance car-to-X communication. There is some over-the-air update, and we would like to adjust our network to handle those transmissions. We could use it also for traffic serialization and many more applications. So thank you very much for your attention.